Hello, and welcome to the Foolproof Way to Eliminate the #1 Cause of Fiber Optic Network Outages webinar from AFL. We have two speakers for you today, Tom Depaolantonio, AFL's Global Account Manager for Verizon, and his special guest, Dustin Munchell, who is a Principal Engineer in the operations area of a Tier 1 ISP. For some background, AFL stands for America Fujikura Limited, and we are part of Fujikura, a $7 billion global manufacturing and technology leader in the telecom, energy, automotive, and electronics industry. AFL is a $1+ billion company that focuses on fiber optic products and services. AFL's product line offers its customers a comprehensive end-to-end solution that starts with fiber optic cable and spans connectivity, equipment to test, install, and maintain networks, conductor accessories, all the way through services and training. And now I will pass it over to Tom Depaolantonio. Tom?
Thank you, Barbara. Appreciate it. And thank you to our audience that they have carved out about an hour's worth of time here with us to go over how do we foolproof and eliminate the #1 cause for network outages. I also want to thank our speaker, Dustin Munchell. Dustin and I have known each other for quite some time.
Certainly, Tom. Thank you for having me.
Absolutely. Thank you. Network outages are bad. There's a cost associated with failures, and there's a range anywhere from, let's say, $150 to $600 per truck roll, and that depends on equipment and manpower. And every time that another truck is rolled for some type of service, profitability goes down, and that impacts a lot of things. The second part of that is SLAs, or service level agreements. And depending on what is going over that network from point A to point B, could be thousands, tens of thousands of dollars, hundreds of thousands of dollars, and even millions of dollars that can be impacted, and then can even be compounded on that based on the amount of downtime there is. Last part of that is we as organizations spend an enormous amount of money to be able to gather customers and bring new customers on. In turn, we also spend a lot of money to try to keep that churn rate down so we don't have unhappy customers. Dustin, what would you like to add to that?
Yes, certainly. So one of the things I do want to add is I believe one of the things that people tend to forget about when it does relate to network outages, that the truck rolls have a cost to them as well as any of the SLAs that we provide to customers, but also the potential damage it can do to our own equipment. So depending upon what that network outage resulted from, whatever that damage to our own network equipment to have it replaced, sometimes that can exceed $20,000, $30,000, $40,000, depending upon if it's a damage to a particular circuit pack. So those network outages do add up, and they actually can cause significant dollar values to the provider when the network is not taken care of appropriately.
I appreciate that. As we move on, so what are some of the leading causes of the optical network failures? And really, when you look at it, #1 kind of sums up everything. It's the contamination of a connector end face. And what we mean by that is that you begin and you end a network with a connector. And depending on the type of connector and the end face is the quality of your network. You also have a few other leading causes, but that's the #1. But from that, you can look at the 2 and really all the way down to #5, and it could be from a poor polish of a connector. It could be damaged prior to plugging in. It could also, there could be a damage of the ferrule and the face, some type of scratch. And when you look at the data here on the horizontal scale, you look at 2 different impact zones. If you look at the cable installer that installs it, and then you look at the network installer, you see where it impacts the various installers here, let's say, whether it's network or cable. Now, as we move on, before we talk about what makes a bad connection, let's take a look at what makes a good fiber connection. And there's really three things that we look at here. And that is, we look at, number one is the perfect core alignment. Now, we know that there's nothing perfect in this world, but as close as perfection can be of a perfect core alignment, that's what needs to happen here. You have to align the cores. The second part of that is the physical contact. How well does it make contact to the other connector that you see coming in from the right-hand side? The third part of that is it pristine? Are the end faces pristine? Are they free of any type of blemish or contamination? Very, very important. Dustin, do you have, you want to talk about the connection on that, or you want to wait to the next slide on the bad connection? Because I know you have a lot of data on that.
Certainly. Let's go ahead and take a look at the bad connection, and then I can add.
You got it. So the next slide, what we're showing is, okay, well, you saw the good connection, but what about a bad connection? So let's say that this jumper on the left-hand side is a dirty connection, okay? And with that, you are now bringing in the next connector, and perhaps this connector was clean. And to the right of that, or to the top right, you'll see that dirt transfers over that. Now, if you go back to the middle of this connector, and as you can see, the impact of it, now that could be in various ways. And Dustin, I know you wanted to elaborate on that.
Certainly. So one of the things that when you have a mated fiber connection like you see here, you're going to have, if you have debris within that connection, okay, I use the analogy of a tennis ball. And say, for example, that bulkhead connection there is a wall, and I'm standing perpendicular to that wall. So if I'm off to the left-hand side, for example, and I held a tennis ball in my hand. So if I threw that tennis ball at the wall, which is a bulkhead connection, and there was some sort of barrier, such as dirt, that ball will come back to me. So as light travels down the core of a fiber, same concept occurs, where when it comes to that bulkhead connection and it has any kind of debris or dirt or contamination, the light is going to reflect back into the core of that fiber, going back to the transmitter. Well, the transmitter doesn't want to see its own light come back. So that is especially true depending upon the amount of power is occurring from that transmitter. So again, going back to my tennis ball theory, let's say that I'm standing maybe 10 feet from that wall, and I whip that tennis ball as hard as I could at that wall. Well, that ball is going to come back and hit me right in the head. That's not going to feel too good. Kind of like light does with a transmitter. So as light leaves that transmitter, and depending upon the power level of that light, once it bounces off of that debris and reflects back into the core of that fiber, it's going to damage that transmitter. Especially when we start dealing with some of these transmitters that can get extremely hot, in some cases positive 20 dB or even 22 dB, especially in some of the amplifiers that we may end up using in the network. So the power levels can definitely be affected by that small amount of debris. And not only will it bounce some of that light back, it'll also have a tendency to maybe burn some of that debris and dirt on the end face of that fiber, and now it can't be cleaned off. It won't be able to come off, and you'll have to replace the fiber jumper or connection. And the other thing to keep in mind is these bulkhead adapters, as we see here, kind of simulate like a patch panel. But don't forget, these fiber connections also are found on the end faces of circuit packs. That is a fiber connection as well. So the closer that debris and contamination is to the transmitter of that circuit pack, the more damage it potentially can do, because that's where your light is the hottest. It hasn't been allowed to dissipate over the length of the fiber.
That's great information. I appreciate that, Dustin. So looking at the single fiber connectors and the applications, what's the target market? What's the target audience here? And if we go back in time, there's been just many different types of connectors, large connectors that snapped in, that had a plunger, that had elongated ferrules, shorter ferrules. Now we're down to the snap and click, which are very robust because they're not recessed. The the ferrule, but it's very close to being recessed, and then the snap and click to make sure they don't pop out. So again, they've kind of morphed over time. What also is morphed, though, in the single fiber is the density. So from going from larger connectors, and this is just in the interior of this slide, is just a real small snapshot of the connectors that are still used today in more of the single, in the single footprint. And of this, if you look at them, that you have greens and blues, and green indicate an angled, and blue indicates a flat polish, or as we look at it, is an ultra polished connector. And really, when you go and look at where's the target at, well, you have central office distribution frames. They're also in the outdoor cabinets, fiber distribution hubs. They're in the industrial environments as well. And then we call them comm room panels, and a lot of times they could be like the ISP MDUs as well as the MTUs. Where else do you see them, Dustin?
Yeah, so we'll see them in a lot of the different panels and outside plant. You'll see them in fiber distribution hubs, and also in drop cases, even at customer locations that are providing fiber connection. You might see what we refer to as an OptiFit connection that would be plugged into the customer's NID, so to speak. But one of the things that I also wanted to point out here with these fiber connections between the green and the blue, and as Tom mentioned, the APC being angled, just real quick, I'd like to go back to that analogy that I had of the tennis ball. So why do we use green versus blue? So if you recall, the blue connector is where I was standing perpendicular to the wall. Think of the green connector if I was standing now at an 8-degree angle to the wall, and I threw that tennis ball at that wall. So what's going to happen? It's going to deflect off of the wall and go off to the side of whatever space I'm in. Same thing light will do. So it'll travel down the core of that fiber, hit that barrier, that debris, for example, and be reflected into the cladding of the fiber. So it's not being reflected back into the core, back to the transmitter. So in a sense, APC is very, helps out quite a bit with the amount of reflection that occurs within a fiber transmission system. And as you can see with the industry today, we're seeing more and more of our LC connectors, because they do accommodate a lot smaller, they accommodate more connections within a single panel space, but also too, we see them quite a bit on circuit pack cards today, especially with our SFPs, small form pluggables, QSFPs, CFPs, etc. They're all pretty much LC, and later on when we talk about MPO connections, they'll be tied into that as well.
That's a great point, and we've seen it between you and I. We've seen it evolve in a very short period of time from various connectors into the MPO, which leads us into our next slide. So the multi-fiber push-on connectors really transformed the environment in the telecommunication sector in such a way that we talk about densification. So it's one thing about taking a single fiber and putting it in a high-density panel, very difficult to get to. Well, now you compound it with the multi-fiber push-on, or the MPO, which has, if you look at the interior of this slide, you're going to see where it has two horizontal rows of 12 fibers. In this particular example, this connector has 24 fibers in one connector. The form factor of this connector, what's interesting about this is that it's not much larger than that of a SC connector. So you're putting 12 fibers, 24 fibers in this case, in one connector. And how that can be seen as a fan out is if you go below the picture, you'll see to the right of it, this is a single mode fan out. Green depicts that it's angled. Then it goes into the fan out, in this particular case, the Lima Charlie LC connectors. And you can also have this as an MPO to an MPO, or an MPO to SCs. There can be just a bunch of different fan outs depending on what the need is. Where you start to see these, where the target audience is really at the beginning of the at the A side, if you will, which is the data centers. And in the data centers, today we're looking at fiber counts that are going up into, as an example, we thought that 864 for a long time was very, very large count, and then came 1728 on fiber cable. We're now producing not only 3456, but 6912, and that's going into the data centers, as well as now you'll see those going from the data centers, the MPOs, now they're migrating into the central offices. They're also down into more of a LAN environment, enterprise side of the business. And we're actually starting to see them in a hardened fiber out in the outside plant. And what's important about that is that these things have migrated so fast in such a short period of time that the amount of fiber and the amount of connectors, even though the connectors might reduce, they still have that much of a quality issue. And I say that not because they're made with a quality issue, but now we have to pay that much more attention to it, because you're not dealing with one connector, one fiber. You're dealing with one connector with 12 fibers, one connector with 24, and possibly up to 36 and beyond. And I think this is where, hey, Dustin, you wanted to add something to this because you're obviously in the thick of it right now.
Certainly. So with these, as Tom mentioned, with each one of these fibers, all 24 of these, for example, they can support up to, in some cases, 250, 400 gig worth of bandwidth per fiber connection. And what makes that very unique is the fact that, okay, so now if we have one pair of fibers that is carrying that much traffic and we have a little bit of debris, and we have some sort of contamination involved, it's going to make it a little bit more difficult to try to ensure that that connection is free and clear to provide optimal service for the rest of the connections. So in the event that you do have to go in there and do any sort of troubleshooting, you end up disconnecting that, and all 24 of those will be disconnected during the time frame that you're doing any sort of your troubleshooting. But where we do start finding a lot of these MPO connections is trunking cables between patch panels. We're starting to see those quite often now from various manufacturers. We also see them on interconnections between circuit packs, so in the same system. So we may have a piece of equipment, a multiplexer of some kind, or some sort of network data center equipment that has MPO connections that interconnect between various cards within the same shelf. So it isn't just to trunk from one site to another, or one relay rack, say, inside of a data center or central office to another. It could be inter connections between the same piece of equipment to trunk traffic between one half of a shelf to another half of the shelf. So it's starting to be utilized a lot more throughout the network.
Thank you, Justin. Appreciate it. So moving on. So what's the first step about taking the guesswork out of whether the connector has been contaminated or some type of defect, whether it was done during manufacture, during shipping, opened up, whatever, that's irrelevant at this point. What we're looking at is, how do you look at it? And as you can see here, you have an inspection scope on your left and a viewing of it. And typically what would happen is you want to take the guesswork out of this. And how do you do it? Well, we're going to see shortly how to, let's say the time it took for the industry to change from more of a subjective viewing scope to that of an objective digital scope. And we're going to see that. But for this, what it's showing you is there's an IEC standard. It's a standard body that looks at different impact zones of the connector. And when you look at it, a lot of times what folks, they think that this black part right here is the core, and it's really not. Right here, this little white part, or kind of gray in the middle, that's the core. That's the 9 micron of a single mode fiber. That's the transmission. The darker part is the cladding. That's the outside of the glass that keeps it intact, right, through the manufacturing. And then all the way down here, you can see some of the gray area right here, or black area. That's the whole connector. That's the 2.5 millimeter ceramic zirconium connector. So all of this right here makes contact, and then it starts to, it's a convex, and it doesn't make connection, but yet if there's dirt on the outliers, because it's electronics, over time, whether it's a day, a month, a year, whatever, it will start migrating to the core. So that's why it's so important to inspect it so that you can see and also take the guesswork out of it by using an objective pass or fail method. So we move on to a very important slide. And Dustin, I know you have information on this. You and I have went back and forth on this for many years about folks in the field getting new fibers in the bags. Bags are completely sealed shut. Rip them open to find that they're dirty, right? And a lot of times we talk about the dust cap being a dust cap, and it really isn't. It's been referred to, the cap on the end of the fiber, as a dust cap for decades. And it's not a dust cap, it's a protective cap so that it keeps the connector end face free of any type of scratches or contamination of some sort outside of just the normal quality of air that we breathe. We breathe 2 to 5 micron dust particles in. There's nothing we can do about that. That's the environment in which we live. At the same time, manufacturing of jumpers are not done in a clean room, and they're done in just a regular environment, which means that there's 2 to 5 micron dust particles that are in the air. And Dustin, again, give or take the average, low and end of the different core sizes of a single mode, it is, how large is a single mode core?
Single mode core, usually around 9 microns.
Yeah. Would it be fair to say that if we're breathing in 2 to 5 micron dust particles, that you could occupy up to 50% of that core just by the dust in the air? Would you agree with that?
Absolutely, and it's not just what can occupy on the core, but also what can occupy, as you mentioned previously, what can occupy around it that can then transfer itself to the core. One of the things that I always use the analogy of, especially when you talk about oil on the end face of a fiber connection, imagine for a moment, if you go back to the days of your chemistry class, or I'm sorry, biology class, and if you were using a microscope and you had your microscope slide in the little slide cover, you had your little droplet of water on your microscope slide, and you drop your little cover. And what happens to that water, that little droplet of water? Well, it spreads out. Same concept that oil can do on the end face of a fiber connection when it gets plugged into a fiber bulkhead. That oil can then spread out as it makes that mated connection, because as Tom mentioned, it's a convex end face. So when they mate, that pressure will, of course, expand the surface area of that fiber connection in that mated bulkhead. So that oil can then spread and transfer itself from the jumper that you're plugging into the bulkhead to the one that it's being received. And same thing with dust particles, dirt particles. Yes, we do not live in a clean environment, whether it's in a data center or a central office or outside plant environment. They all have some sort of dust particles that are in the air.
That's a great point. And one of the things that we wanted to show at the bottom of this slide, you and I talked about this, is that there was a study done of fiber optic connections or connectors. This particular study was LC MPO modules, and brand new out of the box, and over 40% or almost 40% of the samples failed out of the box. So as we go forward, what we're going to look at is the foolproof solution that you can take away. Now, the first part of this is what we want to demonstrate is how to eliminate the number one cause. And the first part of that is inspect and clean every connector every time without fail. You see, years ago when we were dealing with just single fiber connectors and it was just plain old telephone, they were very resilient because it was just pots. They could be dirty. you could plug them in and get a green light. Today that's not what it is today. So there's too much transmission, there's video, there's too many different new technologies that are on connectors. Just because you clean them doesn't mean, without inspecting them, that they're clean, because they could be contaminated, they could be pitted, they could be scratched. So it's very, very important to inspect them. And the same thing is that when you inspect them, it's very important that if you need to clean them, that you do. And here's a perfect environment. We're walking left to right from the outside plant, as you can see how the installs are being done, to all the way to the right of inside a very unorganized cabinet that we see here.
So if I may add to that, Tom, one of the things that I always tell my technicians is, as the data rates have increased over the years, over the last 20 plus years, as the data rates have increased, so has the need for better quality as well as better fiber hygiene. So the network itself is not as resilient to quality of fiber and hygiene as it was 20 years ago, simply because we are pushing a lot more data through it. So always keep in mind that as the data rates keep increasing, so does the need for better fiber hygiene and better fiber quality.
That's a great point. I mean, it's just ratcheting up right now as we go forward. Why does the problem persist? Well, we talked about the data center hyperscale area where deployment of 3456, that's 3,456 fibers, 6,912 fibers in a sheet. That is being done today now. So no longer is that in the future, it's being done now. But also, you don't have single fiber connections, you have MPOs. And one of the things that we were looking at, which is interesting, is we thought that when we had some discussions with some of the hyperscale folks, that the MPOs they're putting in, they're averaging 70,000 MPOs that are shot in one location, and that is not like a one-off. That's just how they're doing business right now. And if you think about it, if you just have 12 fibers per MPO, you're looking at about 840,000 fibers. If there are 24 fiber connections, that's over 1.6 million. So that one connector, or that high density mainframe, is carrying a lot of data. And just by saving 10 seconds per connector, we did an average study, 70,000 connectors, 12 fibers, saving 10 seconds per connector, eliminated 24 days. Another part, you might want to talk about this, Justin, is about the budgets. The loss budgets have really tightened up, and we've seen that, quite frankly, in really probably the last 3 to 5 years, specifically the last 3 years, the loss budget's really tightening up.
Yes, certainly. So you have a lot of cases where the insertion loss between two mated connections, you're always going to have some sort of insertion loss. And as you see here on the slide, it talks about how ORL, or back reflection. So your ORL, or your optical return loss, is giving you an overall average of the amount of light reflection. So every mated connection is going to have a little bit of reflection, right? Every mated connection. So that's going to be two fibers plugged into a bulkhead, mated together. Even at the face of the channel unit, they're all going to have a little bit of reflection. The idea is that we want to reduce the amount of reflection, because reflection can equate to problems within the network, bit errors, damage to channel units, etc. So to eliminate that, the only way to eliminate that in most cases is the volume of reflection typically equates to being dirty connections. Sometimes it can relate to connectors that are not mated correctly, but for the most part, it's a result of dirty connections. One of the other things too that I just want to point out is we have seen before, and Tom touched on this earlier, but we've seen before where you can turn up a fiber span, and it may be fat, dumb, and happy today. But typically when you do your initial test on it, it's an unloaded span, meaning there's no active traffic on it yet. It's just an empty pipe. You may not see the bit errors come across it until you start adding traffic to it. So maybe you don't realize the dirty connections at the time unless you put some sort of load on the span to verify that it's going to operate under a fully loaded condition. So keep in mind that just because you run a standard span and it may come up, as Tom indicated earlier, with your green lights, you want to go ahead and confirm that that span's going to go ahead and operate normally under a loaded condition, because that's where you'll start coming back and finding a lot of your dirty connections.
Appreciate that, Dustin. And the last part of this slide is, as you will see at the bottom, we have bullets on construction, installation, test and turn up, and maintenance. And before, everybody had a certain role, which they do today. But what's more important now of just doing your job or doing your role is making sure that it's done so it's not thrown over the fence to the next group to handle, because then it becomes someone else's problem and it compounds itself that much more. So here's the first step of determining if a connector is clean. And in the past, there's been lots of tools. Even today, I mean, there's lots of tools, but some of these tools have kind of, you know, they've served their purpose. They've done a great job, but it's time to move on. And one of those is really the manual microscope. Now, they're still being purchased, the manual microscope. We have those. The manual microscope, it gives you the opportunity to be able to zoom in at a certain power level and be able to look at the connector. Can you inspect it? The only way you inspect it is subjectively. So it's up to the individual and what they feel might or might not if they can see something. That subjectiveness has went away, and it's become now into the pass-fail standard. We kind of shift now into more of the electronic camera of the scope, the different inspection scopes. You can see here's a snapshot of various manufacturers with scopes. And what you're going to see is, number one, they're safer for eyes because you're not looking into anything that could have any potential harmful rays coming back at you. It's in a camera. One of the things that it applies the standard for pass-fail. So there's no more guesswork. There's no more subjectivity to it. It's fast. It does it within seconds. And then you can store the results, or you can, through the new technology of Bluetooth, Wi-Fi, send it, do all those really cool things. But at the end of the day, there are the products. Now, what's some of the cons? Well, they're going to be more expensive. New technology is always more expensive, but you're also making sure that it's not subjective. You're also making sure that it's addressing your network. So when you do plug it in, it is going to work, okay? And then the last part of that is some of the devices are tethered, some are not, some have a screen, some do not. You know, there's different things. You have to find out what's best for your organization. Now, when you inspect, there's a best practice that you follow, and this is where Dustin's going to really come in, because he's really familiar with and has actually, I think, probably written some of these standards as well in regards to the ICIC, which we're going to talk about. And in this picture here, you can see in the middle is really the MPO with 24 fibers. All 24 have passed. So if the connector passes, Dustin, especially on an MPO, even if it passes like this, would you go back and clean it?
No, only simply because I risk trying to, if I try to take the extra effort to clean something that has been identified as being clean, I risk getting them dirty. The thing that with these MPOs is they can be a little bit cumbersome, I should say, to try to clean 24. So as we mentioned previously, when you have one fiber connection, you're trying to get one fiber end face clean. When you introduce it now and make it 24, now I have to ensure not just one is clean, but every single one of the 24 are clean and fall within the analysis specs. So what can sometimes happen is that, you know, just by cleaning a fiber connection, whether it's an MPO or a single-ended fiber connection, you can make it dirty just by cleaning it. I've seen it happen many, many times. Whether it's your cleaning tools are introducing dirt to it, the action of you trying to clean it and handle the fibers, somehow your fingers slip and touch the end face of the connector. Either way, you can introduce dirt to a clean connector just by trying to clean it. Now, I don't typically risk the idea of cleaning something after the tool has told me that it's clean. If it's clean, okay. After the tool's told me it's clean, I'm going to go ahead and connect it up. But again, if I go through the process of trying to clean, especially with an MPO connector, it can have a tendency to relocate some of that dirt to other end faces. So I'm just having to repeat the process until I do get a green passed indicator.
Appreciate that, Dustin. Thank you. So the investment in a long-term health of the network, you need to invest up front. And that's what we try to help folks understand, is that you want to do this up front because then it alleviates the issues that we showed on the earlier slides about the network outages. And in this particular case, so, Dustin talked about, hey, if it's clean, you inspect it, it passes, connect it. Well, what happens when it's not clean? What's the next step that you have to take? And in this particular case, if you look to the middle and you see the dirty slide above, that's what it would look like in just that gray area there. That's what it would look like to the eye if you had a non-objective viewer. So you would have to say, well, that's obviously dirty. But down at the bottom is where it tells you, going through the software, of the impact zones and where it's dirty at. So then you have to go clean it. Well, what's the next step? Well, we move into the different types of cleaning, and these evolved over time, just like the microscopes have evolved and just like the networks have evolved. And really, through the manufacturing of different types of connectors, they've really migrated to these one-click, and the reason why is because they're very small. You're able to put those in your pocket. You can also not only do the jumper, but you can do the backplane connector. Backplane connector is the bulkhead you're going to plug into. See, before, years and years ago, a technician might walk around to the backside and unplug and clean. And Dustin, I know you're very familiar with that. That's one of the no-nos. Don't go around the backside. Let's do everything from the front so we don't have a drop, right?
Absolutely, because if you end up losing count or you don't count correctly and you're on the backside of a panel, you can do a lot of damage. Secondly, the other thing that I try to remind folks when they're on the backside of the panel, there's one thing that is missing on fiber jumpers on the backside versus the front in many panels, not all of them, but in many, and that's a protected jacket. So a lot of your jumpers obviously are going to have some sort of Kevlar wrap protective jacket to protect them from any sort of excessive bends or movements or what have you, because that glass can be somewhat brittle. They're going to be a little bit more fragile with any sort of movement and activity that's in the backside of that panel.
Yeah, I knew you wanted to jump in on that one because we talked about going on the backside of those panels. The other part of it is we talked about dry cleaning, but then the next step, and we're going to get into that and actually, the best practices as we move forward, but is going into a wet to dry. The first part is you want to try on a dry clean. If that doesn't work, then there are some wet to dry processes. Some are aqua based, some are alcohol based, and some are without either, and they are solvent based, which makes the dirt rise to the top, and then you can use a cloth to be able to remove it. And then there's different sizes depending on where, if you have some tight areas that you have to get into. So there's a big evolution on cleaning. So the first thing that we talked about was when we go is inspect. So use an inspection scope to inspect the end face connector. If it passes it, as Dustin mentioned, connect it. If it doesn't pass, then we have to clean it. And then you clean through using maybe the one-click cleaners, cleaning the interior of it, the bulkhead, as well as the jumper, re-inspecting. And then if it's good, go forward. If it's not, use a wet to dry. If that doesn't work, then we move on to what the next step is. And before we do that, though, here's a good vision of the ICIC, Dustin, that we all follow, right? On the left side is the green for go, and on the red you need to go back and do it again, right?
Certainly. And there is one thing that I do want to touch on, and we continuously speak about cleaning the connectors and cleaning the bulkheads and with whether it's jumpers or circuit packs. And there's one area that I think most folks tend to forget about. And I did for a little bit there, and it just reminded myself about it. And that is our test equipment. Our test equipment is only as good as we treat it. So if we're not cleaning and inspecting our test equipment, just as we do a regular fiber connector, jumper, bulkhead to a patch panel or a circuit pack, we're not doing ourselves any good to go ahead and conduct a test with a test set that has a dirty or damaged connector. So we commonly see when technicians are trying to run some sort of ORL test, for example, that their ORL results are just never passable. So then over time, they just continuously are getting bad ORL tests, and then all of a sudden they grab another ORL meter and they run another test, and lo and behold, the same fiber passes. Only to find out when they inspect it, the one that kept failing the test, they inspect it and find that the bulkhead of that connection is a mess. It's just dirty, it's scratched, it's pitted, it's in dire need of replacement and repair. So this entire time, that technician has been spending time to go ahead and try to run tests with a test set that was ultimately defective. Well, why was it defective? Maybe they weren't cleaning it properly. Maybe they were not storing it correctly. Most of these test sets have the protective cap for that fiber end face. I don't know how many times I've seen those test sets stored without the cap on the fiber end face. So you take care of your gear is going to take care of you. So just remember that it's not just relating to fiber jumpers and circuit packs, etc. It's also your test equipment. You absolutely must treat your test equipment with the same respect that you would with your network.
That's a great point, Dustin. Thank you very much. So moving forward, going through what we've learned with the inspect, connect, or inspect, clean, inspect, connect, what happens if you can't get it clean? What happens if it's damaged? Well, you have various, you can either use we'll say a mechanic connector, which is in this particular case on the left-hand side, a fuse connect, very quick to install in the field with just a cleaver. Obviously, you inspect and clean, and then the other is if you want a factory splice, then you would use a splicer because that's what you're going to need to do. You can't, you don't want to use that contaminated and or defective connector because when you put that into whatever, as Dustin mentioned, your test set, your network element, you're going to transfer either that dirt or scratch that other connector, and then you have a whole different issue at that point. At this level, I think, Gary, there we go. We got Q&A right now. Dustin, first of all, hey man, thank you very much. I appreciate it, and appreciate the time that you spent with us, and then also the audience. Want to thank the audience for spending time with us, and we do have some questions, but if you don't know how to send the questions, look to the right on the panel, and there's a question tab. You can type in your questions. We're going to wait a moment. We got a little bit of time here. We'll wait maybe a minute or two for anybody that has questions. There's a few that are popping up right now, and Dustin and I will take those. At the same time, there's 3 documents, there's 3 handouts that our folks have put on there for you. If you choose to want any one of those or all 3, you may download those at your convenience. This has also been recorded, so should you want to go back and listen to any part of it, you may do that. And then got a couple more questions coming in. Dustin, I'm going to throw some your way. So
all right,
first one
sure.
is, let's see, typically, how does the equipment usually show or indicate dirty fiber connections? You want to pick that one?
Yeah, certainly. So yeah, the equipment itself, what you'll typically see is it varies from equipment to equipment, but a lot of times you'll see where it'll show bit errors. You may have traffic that's indicating a certain volume of bit errors. Also, too, a lot of the equipment today have the ability to measure loss. You'll get your standard, which has been a common response, like a loss of signal, loss of frame, etc. But sometimes you'll see them indicate bit errors. But more importantly, it'll also give you some sort of light indication where you can actually look at the volume of light that's coming into it and then do a span analysis as far as what your loss budget might be or what your expected loss should be. Another thing that is now happening in a lot of equipment today on some of our larger spans is they have their own built-in OTDRs, which is certainly beneficial from the perspective that now we can try to identify exactly what or where the trouble may be. So some of that equipment today will have that ability to go ahead and pinpoint if it is a dirty connector and what connector might it be. Is it a bend in the fiber and where that bend might be located? Is it a bad splice, etc.? And in a lot of cases, those are non-intrusive so that they're not causing outage when we go through and conduct the test. But yeah, usually the MUX will tell you. It's just a matter of being able to interpret it accurately and identifying where exactly that may be as far as where your trouble is showing up.
Appreciate that. There's this one I'm going to throw your way as well. As a service provider, how can I convince my teams to take cleaning and inspection of fibers seriously? Great question.
Yes, that is. So for many years, I've conducted a lot of training within different environments within network data center, outside plant, and it's been an interesting transition to try to convince the folks from the days of just cleaning a fiber with our shirt. We were always kind of had the old school mindset that, yeah, you just wipe the fiber connection on your shirt and you'll be good to go. And for a while, we did get away with that. And as I mentioned earlier in the call, I made reference that, as the data rates have increased, and this is where, the one thing that trying to convince the field and convince the workforce that it's imperative to do that. As the data rates have increased, I just can't emphasize that enough. So has the need for better fiber hygiene and fiber quality as well. So it's really important to make them understand that we're now starting to try and push more and more data rates through these pieces of glass, in some cases that have been in the ground for 20 plus years. So it becomes even more important to ensure that the hygiene and the cleanliness, the hygiene and the quality of the fiber that we currently have in the plant, as well as within our data centers and central offices, is as clean as we can make it. The other part of that is you never want to go back and do the same job twice. So if you're going to do it right the first time. Don't try to go back and do it a second time, a third time, a fourth time, and then only to find out that maybe you just had a connector that was dirty and it would have took, instead of having 3 or 4 or 5 repeats, maybe it was a matter of just going ahead and taking an extra 30, 40 seconds to go ahead and clean and inspect that one fiber end face instead of having to repeat to the same job 2, 3, 4 times.
Excellent, man. Here's another question. I'll take the first part. You can take the second as a service provider. So, what sort of damage can dirty connectors cause? So, as a test equipment manufacturer, as well as a passive optical maker, look, at the end of the day, if you, as Dustin went over this earlier in the slides, if you take a jumper and it's dirty, you've inspected it, but it hasn't been cleaned. It could be pitted where it is defective at that point. With the amount of pressure that it applies through the bulkhead, and you insert that into a piece of test gear, then now the test gear has basically taken on whatever that dirt or potential scratch from that connector defect onto the pigtail that's within the test equipment. Therefore, the network, when you're testing it, can only be as good as the tester that you're using. So if that's contaminated, if there's a defect or a scratch within that pigtail, then your network can only be as good as the test equipment. So therefore, that's why, as Dustin mentioned early on, it's very, very important to be able to take care of your test equipment. At the same time, when you plug into modules, that it's just transferring. It's not only dirt transferring, but because of the amount of pounds per square inch through, let's say, an SC or an LC connection, or even an MPO, and the alignment, it affects it in many different ways than just transferring dirt, but through the signal processing and such. So I'm going to throw you want to sum it up more as a service provider, though, the impact that you've seen?
Yes, certainly. So yeah, and one of the things that I just want to focus on is that when you deal with, if you do have connectors that are ending up being dirty or damaged in the field, a lot of times, what can they cause to the network? Well, besides the impact on customer outages, which is obviously the most important, the other side effect of that can also be, in a lot of cases, damage to your own network equipment. So if you, as I mentioned previously regarding some of the higher powered amplifiers that we currently have in a lot of these networks, they can damage those cards, and you can have a case where a amplifier that may have 18 to 24 ports is now defective because one port is bad, and that was because maybe there was too much light being reflected back into the core of that fiber and being reflected back into that transmitter. And now that transmitter on that single port has burned up. So now you got to take time to go ahead and replace the card. Well, that costs money. And same thing with the damage to things like the individual channel units that may get burned up, or the SFPs and QSFPs and CFPs that are involved in network element equipment. They end up becoming damaged and have to get replaced. So, and then you also typically, or not typically, but you also can run into potential damage on the actual fiber jumpers themselves, and then those incur a cost to have replaced. So the damage that can be presented within a network can be, more than just whatever the can be a result to the customer, but also could be something that's going to affect your own network element equipment within inside your data centers and central offices.
Thanks, Dustin. Appreciate that. We're almost, we got a few minutes left, but we have more questions than we do time left. So let's pick, I'll pick two more, and then we'll close for the day. So this one will lead into what you and I have talked about going forward, but other than fiber hygiene, what other preventative measures can a field technician take to reduce fiber outages? So other than fiber hygiene.
So one of the things that I see with that you might run into is things like proper fiber routing. If you're going to route fibers within a panel or a piece of equipment, you want to make sure you're routing it as properly and neat as possible. Most of this equipment has its own built-in fiber routing trays, and they have their own fiber routing rules that are put in place. Many network providers have their own fiber routing rules. Even from back in the days when we used to run copper, I don't, if you ever go past a old copper panel or inside of a old data center or central office, and you look at an old copper frame or anything like that, you can kind of figure out which ones were routed, correctly versus those that may need a little work. But in some cases, it's whenever you just make the rush effort to go ahead and put in a particular jumper, or you may not have the right length jumper on hand, or whatever the case might be, the end result over time will be, a bird's nest. You'll just have a big tangled spaghetti mess of fiber jumpers or copper jumpers or whatever type of data circuit you're running, whether it's Ethernet cables, what have you. But you may say to yourself, well, why does that, okay, so how is that affecting the customer? Because within fiber, it can be affected by excessive bends. Some of the newer jumpers are a little bit more tolerable to that today than they are maybe 5-10 years ago, but the jumpers themselves are not going to be very tolerable to excessive bends. You also run into the potential problem that if they get pinched inside of a door or what have you, they could cause a macro bend, or you might even damage the fiber itself and put a break in it. You also run this risk of, with some of the jumpers, depending upon how much of a protected jacket is around it, by breaking the jumper altogether. Another area that you might run into is improper or just sort of poor routing and handling practices within splice cases and splicing practices. So normally whenever you conduct a fiber splice, they sit inside a little tray and they get routed around bend radius spools, and you want to make sure they're placed in there correctly, and then test it after you conduct your splice. The reason for that is that by the time you're ready to go ahead and start turning up services across that, and if it's a buried splice, for example, now all of a sudden you find out that maybe one of those splices or one of those jumpers inside that splice case are bent beyond the bend radius. So now you got to send somebody back out there, and they got to dig up the splice, and they got to go ahead and relieve that bend. So making the effort to go ahead and making sure that you have all of the proper training and all the proper tools on hand when it comes to conducting your splicings, routing your fibers, etc., as well as cleaning and inspecting, is going to help you in the long run.
Global.com. We thank you for your time. Have a great Tuesday.